Yeah, let's get started. So today we are going to talk about linear feedback shift register. So here, linear feedback. So it is shift register having linear feedback. So when I say feedback, what comes in your mind? So output is fed back to?
Output is feedback to the input.
Right. So like in the case of SR flip-flop, right? Remember the SR flip-flop, your output was feedback to input, right? Like this. Okay, like this, right? You have the flip-flop. So this is the output feedback to input. This is the output feedback to input. So output connected to input, that's the feedback. Okay. So as you can see here, right, these are the outputs. So this is the flip-flop. How many flip-flop we have? 1, 2, 3 flip-flops. This is the output of the first one. This is the output of the second one. This is the output of the third one. And these outputs are fed back to input here. Okay. This output is the input to those flip-flops. And this feedback is linear, okay? This is linear feedback. Okay, so how do I know this is linear? Let me show you how. So here, as you can see, this is the linear one. So what is this is the feedback loop, right? This is the feedback loop. This is the feedback. How is this feedback generated? It's S0. How do I represent this? S0 plus XOR, right? S0 XOR S1, meaning this S0 and this S1. These are the two inputs to the XOR gate. This is the XOR gate, right? XOR. Okay. So meaning the feedback is generated by XORing S1 and S0. So this kind of feedback is called linear. So if you generate the feedback like this, then that would be non-linear. See, what is the difference between these two? You have the non-linear term here, right? So this one, there's a, you know, this, what is it, like x, like x squared, right? See, this is just like x plus y. This is just like x squared plus y, okay? This is something like x plus y. This is something like x squared plus y, which is not linear, right? This is not linear. This is linear. So that's what I meant by linear feedback. Okay, so this is the linear feedback shift register. All right, oops. All right, this is the linear feedback shift register. Now, so previously we had the, we used the shift register for the, what did you use the shift register for previously? last time, if you remember. You know, shifting data left or right, you know, that kind of thing, right? Okay. Now here, we'll be talking about the generation of pseudo-random numbers. Okay. So you understand what's a random number, right? Random number is easy to understand, meaning any number, 0 and 1 in our case, right? Generated in random, right? We don't know what will be the next outcome. It could be 0, it could be 1, you know, again 0, again 1, 1, you know, it could be anything, right? That's the random number. So what is pseudo-random number? I'll give you an example in the next slide, okay? So for now, just remember this is pseudo-random number. We want to generate, if you want to generate pseudo-random number, then we use linear feedback shift register, okay? As I explained earlier, feedback function is generated by XOR gate, okay? And in my case, I have 3-bit LFSR, okay? Linear feedback shift register, 3-bit. So we have one here, another here, 3-bit, right? So depending on how many bits you want, you have to keep adding the number of registers. Okay. Now your S in feedback, you know, input of the register is given by this formula. In our case, okay, depending on what you want to do, you can choose one or the other. Okay. So we have chosen this for some reason. So I'll explain that in the next slide. Okay. So you can choose different feedback system here. But one thing you have to choose here, be careful here is when you start the shift register, linear feedback shift register. Remember you have preset and set and preset button, right? Clear and preset. Okay. So you shouldn't start with a clear one. You should better you start with the preset one. Okay. When you start the system, you hit the preset button. Then you start doing, you know, don't hit the clear button for a region. Okay. So what happens if you set the clear button, because you have 0, 0, 0, right? Okay. So this feedback system, this feedback shift register does not work if you have all zeros. Because if you have 0, you start with 0, okay? You don't get anything here. You always get 0. Next cycle, you'll get 0. Next cycle, you'll get 0. Third, you know, fourth cycle, you'll get 0 again. You'll never get rid of zeros, okay? That's what happens. How does that happen? We'll discuss it, okay? All right, let's see how it works, how the shift register works, then we'll talk about why this 0 is excluded, okay? Let's say we hit the preset button, right? So the thing is we have 1, 1, 1 everywhere, right? 1, 1, 1. Okay. Then what is so now in the first cycle we have 1, 1, 1. We started with this one, okay? Then second cycle, what happens is, what is the input? What is the input to this guy here? Help me here. What is our feedback loop? This is my feedback loop, right? Okay. So S0, S1, meaning this is the kind of truth table we have, right? This is the truth table. So what do you get here? S0, when you have this guy here, 1, 1, 1. So this is your 1, and this one XOR together, right? So this means we are looking at this guy here. Okay. So here When 1 and 1 XORed, then you get 0, right? Then 0 is here now. That 0 is here. This 1 XORed, you get 0. And this 0 is fed. 0 is fed here. What happens is this 0 replaces this 1. Now this becomes 0. This 1 replaces this 1. Again, you have 1. And this 1 replaces this 1. You have 1. So you have 0, 1, 1. 0, 1, 1. Does it make sense so far? Does it make sense so far?
Yeah.
Okay. Now what happens in the next cycle? Now when you have the second, then what happens is the next thing is what is the input to the in the next cycle? These two XOR together again, right? So it gives you 0 again. And this 0 pushes, you know, this guy is again back. So this guy is out, this guy is out now, this guy is here, and this guy goes in here, and this guy is here. So you have 0, 1, sorry, 0, 0, 1, 1. Okay. So we have done that, right? So then what happens here? You have to XOR this guy and this guy. What do you get? This and this XOR is 1, right? Now you have this 1 goes on in the front, then these zeros. See, that's why this is called shift register. Sorry. This guy is called shift register because of that. Okay? Because this is shifting the digits from left to right in this case, right? See? This is shifted here, this is shifted here. That's why we call it shift register, okay? Now this one comes in the front. Now, when you XOR these two guys, what do you get? You get 0. Now this 0 comes in here, and this 1 is here, and this 0 is here. Then 1 and 0 is 1, right? So 1 comes in here, and this 0 goes here, this 1 goes here, and this guy vanishes. Similarly, this guy comes in here. You understand the logic, right? Okay. Then finally you will have 1, 1, 1 again. Look, in the process, what did you start with? You started with 1, 1, 1. Remember? You started with 1, 1, 1. Okay. See, you started with 1, 1, 1. Now you ended up with 1, 1, 1 again. The same cycle goes through again. Same cycle again and again. Then what are the inputs you get? You get those inputs only. See, this repeats again and again. Okay, so these are the random numbers, right? These are the random numbers. This is 0, 0. We don't know, right? 0, 0, then 1, then 0, then 1, 1, 1. These are the random numbers. But after that, it repeats again. Okay, so even though they are random, it's not completely random. They are kind of pseudo random. Okay. Does it make sense? Okay, so these are called pseudo random numbers. So now we have the random number is 0, 0, 1, 0, 1, 1, 1. Okay, 0, 0, 1, 0, 1. So this number is called pseudo random number. Okay, so now the thing is, what is the length of the random number you can get? So what is the length here in this case? 1, 2, 3, 4, 5, 6, 7, right? So how many flip-flops we have? We have 3, right? N equals 3. So maximum length, this is the maximum length is 2 to the 3 minus 1, which is 8 minus 1 equals 7. Fortunately, we got the random number of maximum length. Fortunately, we got, because the maximum possible is 7, and we got 7. It doesn't mean that we always get the maximum, okay? Not all the feedback gives us maximum length. Our particular feedback, right, S1 plus S0, XOR S0, this gave us maximum. But if you choose some other different feedback, it might not give you maximum length, okay? That's what I'm saying. So what is the use of this feedback shift register? They are used in cryptography, wireless communication, spread spectrum broadcasting, and global positioning, okay? So, and you know, there are this kind of, this is the use of LFSR, okay? Linear feedback shift register. Guys, question here.
So if we had 4 inputs, like an S3, we could have 15 pseudo-random numbers, or 15 pseudo-random numbers that we could choose from.
Maximum possible, yes. But yeah, so if you have 4, let's say you have number of flip-flops equals 4, right? Then you have 2 to the 4 minus 1 equals 16 minus 1 equals 15. You're right. Okay, the maximum possible is 15. It doesn't mean that you always get maximum, but if you choose the, you know, the input properly, okay, then you might get up to 15. That's the maximum. Does it make sense?
Yeah, thank you.
All right. Yeah, good question. Okay, go ahead.
If the pseudo-random number repeats after every 7 cycles, then isn't it not random if it's just the same thing coming out?
Yeah, that's why we call it pseudo, right? You're right.
Pseudo.
Yeah, that's why we call it pseudo. So
Gotcha.
it is random up to 7, right? We don't know what it comes, but after that we know what it is, right? It's the same thing again. That's why.
So it's not. Sorry.
Go ahead.
It's not necessarily going to be 0010111. It could be any number, but it's going to be repeating after 7 cycles.
No, like for the so you are here, right? Suppose what will be the next number? What is the next digit? It could be 0 or 1, in this case 0. What is the next digit? It could be 0 or 1, in this case 1. What is the next number? It could be 0 or 1, is 0.
Yeah, so the first 7 can be like any combination of 0 1s. It's just going to be repeating.
Yes. So
Okay.
before you start, we don't know what comes here, right? Do you know what
Yeah.
comes here? You don't know, right? So that's why this is random. But after 7, you know what is going to be next cycle. It's the same thing
It's
again.
going to be the same thing. Okay.
Okay, that's why we call it pseudo-random.
I got you.
Thank you. Yep. So yeah, so yeah, now, okay guys, can somebody help me? Can anybody volunteer reading this page for me? I'll read the next one by myself. If you can volunteer, somebody can volunteer to read it for me, I'll be grateful.
I can do it.
If you'd like.
Okay, please.
LFSR sequences are widely used in radio technology, particularly in the context of spread spectrum applications. Their purpose is usually to provide a way to distinguish or synchronize signals, and sometimes to provide a level of cryptographic security. In CDMA technology for cell phones, for example, data is overlaid on LFSR sequences, and sequences other than the one intended for a particular receiver seems like noise which can be ignored. As another example, the Global Positioning System, GPS, works by having 24 satellites each transmit maximal length sequences from different length, 10 LFSRs. Position is deduced from the arrival times of signals as determined by the relative phases of the LFSR sequences received. GPS P code apparently uses much longer LFSR sequences and repeats only every 267 days. Before May 2000, it was used to add unpredictable timing errors to ordinary GPS signals.
Okay, thank you so much. So
Mhm.
I don't know how much did you get it from here. So we have a big book for this use of shift register. So, you know, if you understand at least like 5% of it, so I'll be happy. All right, so, and next, this is the example of cryptography, okay? So this is one of the examples where public key, this is called public key cryptography, where different keys are used for encryption and decryption. So as you can see here, so they have used the LFSR here, a linear feedback shift register here, okay? And as you can see here, this is the public key to encrypt, and this is the private key to decrypt, okay? So this is also a technology where LFSR is used. And these are the different ICs of useful shift register. Okay, this is the IC number that could be found in the lab. Okay, these are the different IC numbers. So this is the different function of those ICs. Okay. Now let me talk about the multivibrators. This is important because we are going to use this in our lab next week. Okay, so we'll be using LM555 timer. Okay, so this timer can operate in several modes. For instance, most popular are astable and monostable. You know what those are, right? So we did that in the beginning of this chapter. So what are the astable and what are the monostable states or modes? But in the lab next week, we'll be doing astable mode. Okay, so timer. When I say timer, what is the timer? Because what is the you get the analog signal, right, in the AC, right? AC is analog, right? Okay, the thing is, so since now we have done a lot of until now we have done a lot of study that we need triggering, right? Remember, we need triggering. So sometimes you need positive A's, sometimes we need negative A's depending on the device we are using. Okay. So now the thing is, what I meant here is we need some kind of device that gives this kind of wave, right? Okay. So we need this kind of wave. So meaning we need a device that produces this wave. Okay. That device is the timer. Okay, that's called timer. The timer, the output of the timer, this is the output of the timer. Okay, we generate this kind of waveform. Okay, so obviously this is astable mode, right? Because it goes from low to high and come back to low again, then goes back to high again and comes back to low again. You know, it's astable. It's not stable, it's astable. Okay, so now yeah, so we'll be this in the lab. Okay, so let's see how it works. Okay, so there are different, various kind of timer. There are different kinds of timing device or timer, I would say. But this 555 timer, 555 timer is the versatile device, okay? It is very versatile. The advantage over other kind of timer device is that this can obtain long periods with relatively small capacitor, okay? So we can obtain long period with relatively small capacitor. Because when you have the device, suppose this is a timer, 555, right? Okay, then you have to connect a resistor, capacitor, something like that, okay? So with relatively small capacitor like this, we can get a longer period. Okay, that's the advantage of 555 timer. Okay, that's why it is very versatile. Now this is what the configuration looks like here. This is the configuration of the 555 timer. So what is inside, right? So we haven't shown everything inside because we say comparator here, COMP, comparator, compare. There's something that compare, right? That compares. Okay, that's called comparator. So we have another comparator here, and we have amplifier here. See that? Then we have what is this guy called again? Flip-flop, right? We have flip-flop here. Okay, and we have register here. See, we have one register here, another register here. They have same value, exactly same value. 3 register here. Then we have so this is called transistor, by the way. We haven't done that yet. So for now, I simply call it transistor. But I will be talking after chapter 5. We are done with digital. Then we'll go to the analog part. Then we'll talk about transistor. Okay, this is transistor, and there is another transistor here. Okay, so these transistors, inside this transistor, the structure is messy. Okay, inside this guy, the structure is messy. Inside this is messy. Inside this is messy. Okay, but we have hidden a lot of parts already here. Okay, we have already hidden lots of parts, but still, it is still messy, right? Even though we have hidden a lot of stuff, it's still messy. So we don't have to know everything inside. So if you understand this, that's good. Okay. Now there are different pins here. There are 8 pins. So we had in 181, right? Chip, the big chip. How many pins we have? We had 24. Okay. So in this chip we have just 8 chip. 555 timer. We have just 8 pins. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, there are 8 pins. So we don't have to know everything about every pins. But the thing is here, so I'll talk about most important ones. Okay, so here we have the threshold pin, which is 6. We have the trigger pin, which is 2. We have the discharge, which is 7. We need output, obviously. Then we need 8. Okay. So what is this 8? 8 is VCC, meaning you have the supply voltage here, right? So do you remember for 181, what is the supply? What is the supply pin? 24. Pin number 24 is supply. Is this right? Correct me if you are wrong. Do you remember? I think that 124, chip number 24 is the VCC, but in this case, chip number 8 is VCC, okay? So from VCC, suppose you supply here 9 volts, for instance, right? Then what is the voltage across this guy? Voltage here, right here. So voltage here is 9 volt, right? From here and the ground. Ground is here. So voltage difference between these two guys is 9 volt. This is 9 volt. How about if I measure the voltage here and here, what is the voltage across these two guys? So what will be there? Guys, help me here. If it is 9, if this guy gives you 9, what does this guy give me? Voltage divider.
Would it be 3? Since it's 2/3, or 6 since it's 2/3.
Yes, 6 volt. Yeah, thank you. 6 volt. Now, if I take the voltage here, then it will give you 3 volt. So that's why this is called 1/3 point. This is 2/3 point. We are just using the voltage divider rule. Remember voltage divider? Okay. All right. So we know that this is 2/3 and this is 1/3, right? Now now we have two comparators, right? So one comparator is here, the other comparator is here, right? We have two of them. So what is the input of this comparator? You have two inputs, obviously. I call it B minus. See that, did you see minus sign here, right here? Small minus sign, that's B minus. And you call the plus, I call B plus, meaning voltage here is B plus, voltage here is B minus, okay? And voltage here is B plus, voltage here is B minus. So now, so this guy will give me B plus. When B plus is greater than B minus, it gives you 1. That's how comparator works. Does it make sense? So when B plus is greater than B minus, output is 1. Otherwise, output is 0. Otherwise meaning B minus less than B plus, it gives you 0. Okay. So this is 1, otherwise 0. Okay. So this guy, so now similar, this guy also works the same way. Okay. This is exactly similar comparator here. Two comparator, right? Okay. Now, if it is 9 volt, right? If it is 9 volt, so what is the voltage here? 3 volt. Okay. So what is this B plus? B plus is 3. Okay. Then if this trigger is less than 3, so what is the output here? Guys, you have to help me here. If the trigger is less than 3, what is the output here? 1 or 0?
0.
0. Because you'll get 1 only when B plus is greater than B minus. Your B minus is less than 3. It means your B plus is greater than B minus, because your B plus is already 3, because you supply 9 volt here. So in that case, hold on. What is the question I asked? So when I'm supposed to ask this question, okay? Let's see. When the voltage here is less than 3, that's what I'm asking. Meaning when B minus is less than 3, B plus is already 3. What is the output of this guy? Let's say, why do I call it, let's say, less than 3, I just give you a number, okay? So let's say voltage here is 1 volt. This is 1 volt. So then what is the output here?
1.
This is 1. Maybe did I ask something else? I'm supposed to ask this question, okay? So this gives you 1 because your B plus is greater than B minus. 3 is greater than 1, that's why it gives me 1. Meaning your R will be 1, reset. Remember RS flip-flop? RS flip-flop. In the RS flip-flop, when R is 1, what is the output? What is the output here? When R is 1, output is 0. Okay, in the RS flip-flop, reset is 1 means it resets, okay? R equals 1 means it resets. That's the meaning. R equals 1 meaning it resets. S equals 1 means it sets. That's the meaning. R equals 1, it resets. S equals 1, it sets. That's the meaning, okay? So R equals 1, meaning it resets, means it gives me 0. So this guy works in such a way that when this guy is 0, this is always 1. Okay, I don't want to go in detail, okay? This guy, so in this case, my output is 1. When this is 0, this guy works just the opposite. I get high voltage like this. Okay. Okay. So now another thing I want to say here is when this guy is 0, see that when this guy is 0, this transistor also 0. See that? This is called transistor, right? You don't know about this guy. But when the base is 0, okay, this act as, this is actually switch, okay? When this is 0, this guy is closed. That's how it works, okay? We'll do that in the analog portion. When this is 0, it is closed. When this is 1, this is, I should have said open. When this is 0, this acts as open switch like this, open. Okay. When this is 1, this acts as a closed circuit. This is 1, this is 0. Okay. In this case, this is open. This guy is open here. Okay. The switch is open here. This acts as open. Does it make sense? Okay. Now let's go back to the other comparator now. So other comparator, what is the voltage of what is the voltage? What is B minus for the other comparator? B minus is 6 volt, right? Because it's connected here. See that? It's connected here. That's why B minus is 6 volt. So this guy, when does this guy gives me 1? Help me. When do I get this 1 here? When this gives me, this threshold is greater than 6 volt, right? Does it make sense?
Yeah.
When threshold is greater than 6 volt, then you get 1 here. Does it make sense? When this is 1, let's see what happens. Your S is 1, right? When S is 1, set, right? Set is state. Then it gives me 1. When it gives me 1, then this guy is now closed. This acts as short circuit now. This switch is closed now. And when this is 1, I get 0 here. So that's why my voltage is like this now. So does it make sense how the output works? Before I go to the next slide, please ask me a question or questions. So far, so good.
Yeah.
Mm-hmm.
Okay. Now in the in the lab, what we do is we use this as a astable mode, right? As I said earlier. So this guy, and these guys, they are exactly same. Okay, but I have some extra here. See, I have something extra. RA, RB, and C extra here. Okay, so if you want to use LM555 timer as astable in astable mode, right? Then you have to have these three components here. You have to add them there. Okay, and also you have to have the connection like this. So what is the connection here? So your 6 and 2 connected. See, this 2 is connected to 6. This 6 is connected to 2, right? So these two are connected. Then, so this 6 is 6 or 2, both of them, right? 6 or 2 connected to C, capacitor. So this guy is connected to capacitor here, and the capacitor is connected to ground. On the other hand, the 7 is connected to, what is 7? 7 is connected to your register, and this is connected to VCC here. And also 6 is connected to register, and that is connected to this guy, right? So this is your RB, this is your RA. So this is, when you have the connection like this, then your 555, this 555 acts as astable, works in astable mode, okay? Okay. Now the thing is, this threshold and trigger, both of them are connected now. Okay, this 6 and 2, they are connected. So I call it B2. How about that? The voltage across the trigger is B2. Okay, voltage across the chip number 2. Sorry, pin number 2. Okay, I call it B2. When B2 is 0, initially there is no voltage, right? So we start with 0. Okay. So what I'm saying is I'm going to supply BCC here. Initially, BCC is 0, meaning this is at 0 volt. This 2 is at 0 volt. This is 0 volt in the beginning, meaning this is 0 volt, right? Okay. Since this is 0, right? So what do you get here? 1 or 0? You get 1 or 0. This is 0, right? So B plus greater than B minus gives me 1. Remember? So this is 0, B minus is 0, and B plus is 3, right? For instance, let's say 9 volt, right? So In the beginning, this gives me 1. The reset is 1. Does it make sense? Reset is 1, meaning it gives me 0. What does this do? This is open or closed?
Open.
This is open. Okay? Meaning the current does not pass through here. See that? This is open. Does it make sense? This is open. So if you send the current from here, then current doesn't go here. This is open. What does the current do? Current passes through RA, RB, and finally go to C. So then the capacitor will be get charged. Does it make sense? What did I say? When you begin with voltage equals V2 equals 0 here, right? This is what you do all the time. Your initial voltage is always 0. Okay. So then you start from 0, right? Let's say, I don't know. What do I call 0? So let's say it's 1 now, okay? It's slowly going to rise, right? Let's say, so this is 1 volt, then 1 volt, this is 3 volt. Okay, this is 1 volt, this is 3 volt, this is 1 volt, then this is 1. When this is 1, this is 0. When this is 0, this is open. This is open means this guy is open. Okay, when this guy is open, then current, all the current flows to here and it charges the capacitor. Okay, at the same time, this is 0. That's why this is 1. You get the high. You get the high there. Okay, this is high. Let's say this is high, H. Then next time you will get low here. Okay. Now, what happens when the trigger is above? Let's say now the voltage is slowly increasing. Let's say, right? Then let's say so before until 3, right? Until 3 volt. So this stays 1, right? Okay, until 2.9, I don't know. Until 2.9, this is stage 1. How about if it is, let's say 3.1? What happens? Will this be 1 or 0?
0.
This is 0, right? This is 0. So R is 0. Okay, when this is 3.1, right? Remember 2 and 6, they are connected. What is the voltage here? 3.1 also. So if this is 3.1, this is also 3.1 because 6 and 2 are connected. Do you see that? 6 and 2 are connected. That's why in this case, will this give me 0 or 1? Remember this guy is 6, right? This guy is 3. Will this give me 0 or 1?
0.
0. Now your S is 0, R is 0. So what is that state? Holy state. That's why your output stays high up to 6 volt. Until this guy reaches 6 volt, your output is high. Now what happens? It reaches 6 volt now, or greater than 6 volt. So let's say this guy is now greater than 6 volt. This guy is greater than 6 volt. So this is, let's say 7 volt, right? So this is 7 volt because they are connected. So what does this give me?
1.
1. What does this give me? This is 3. This is 7. This gives me 0. This gives me 1. So S is 1, R equals 0. This is steady state, right? This is steady state. So it gave me 1 here. When this is 1, this gives me 0. Now I start getting low voltage there. Okay. Now how about when this is 1, what happens to this guy? It closes, right? Remember this closes? When it is 1, it closes. Meaning this guy closes now. See, this guy closes. Do you see that? This guy closes here. Then capacitor no longer charges. It goes through to the ground. Remember, this 7 is connected to ground. See that? 7 is connected to ground now. See that? 7 is connected to ground. That's why the capacitor discharges through RB. So what I'm trying to make you understand here is this thing here. While charging, you have to understand these two things here. This is the whole idea of this discussion. So during charging, the voltage remains high. Output voltage, right? See this output voltage remains high. While discharging, output voltage remains low. This is charging process. This is discharging process. So when the capacitor discharges, it discharges through RB. See, it doesn't go here because the ground is here. It discharges through RB. Okay, let me write this down. Discharging through RB. When the capacitor charges, it charges through RA and RB. Charging is through RA and RB. If you understand this, you don't have to understand more than that. Okay, so charging is through RA and RB. Discharging is through RB. Guys, question here. I'm ready for question.
So I have a question, but it's not about like what you were just talking about. So the proportion of like 2/3 of the voltage and 1/3 of the voltage, is that the same regardless of what input your voltage is?
Yes, because because this is the. So let me tell you here. So this is very easy to make you understand. Because this is like this, right? Let me show you. This can be written like this. So how many registers are there? 1, 2, 3. This is R, this is R, this is R, okay? So, so this is 9 volt. What is the voltage between these 3? 9? So this is 9, right? There is no doubt. Now, what is the voltage between these two?
6.
How do I know? Because what is the register here? R plus R, 2R. 2R. Then what is the total register? R plus 2R. Then this 9. So what do you get? 2R over 3R times 9. So 3 times 3, 9. What do you get? 6.
Gotcha. Okay.
Okay. Similarly, what is the voltage across this guy then? Here.
3.
So R over R plus 2R, which is, 1 over 3 times 9 equals 3. This is voltage divider rule.
Gotcha.
Okay. Yep. Thank you. Thank you for the question. Yeah. Yeah, you had to wake me up sometime. All right. So we came to the conclusion that while charging capacitor, it charges through RA/RB. In that case, the output is high. This is output, right? While charging capacitor, it charges through RA and RB. In this case, output is high. When discharging, it discharges through RB, and your output is low. This is your output, right? This is your output. Output is low. So charging high, discharging low. Charging through RA/RB, discharging through RB. Okay. Now this is the equation we are going to derive, and this will be used in the class, in the lab. Okay. So this is the conclusion we have. Output is high and low while the capacitor is charging and discharging respectively. That's the conclusion we have. Now V2 here, V2, where is my V2? V2 here. So V2 meaning this guy here. V2, what is V2? So V2 is V2 is the V2. This is my V2, right? This is my V2. V2 is the V2 is the, help me here, voltage across the capacitor. Okay. So because this V2 is meaning the voltage at pin 2. So which is voltage across the capacitor. Okay. So when I say V2 is the voltage across capacitor. Okay. So what is the voltage across capacitor during the charging process? In the charging process, V2 is equal to VCC 1 minus T, 1 minus E, negative T over RC, right? Remember we did this in your first chapter. Okay, so this is charging the capacitor. Now, what is the time it takes to, what is the time taken by capacitor to charge from 0 to 1/3 of the VCC? So how do I do that? So B2 is 1/3 of BCC. So that's what I did here. This is 1/3 of BCC. Then, so from here, okay, this is 1/3 of BCC. So this is 1/3 of BCC equals BCC 1 minus E negative T over RC. So BCC cancel out. Then what do you get? 1 over 3 equals 1 minus E to the negative T over RC. Then you get E to the negative T over RC. This equals 1 minus 1 over 3 equals 2 over 3. Okay. Then you take the log on both sides, natural log. So what do you get? You get negative T over RC equals ln 2 over 3. That's what you get, right? Here. Then what is T1 from here? T1 is negative RC ln 2 over 3. Then this can be rewritten as RC ln 2 over 3 becomes 3 over 2. Doing that, your minus sign becomes positive, right? You know the log rule, log properties. Now your T1 is this. Similarly, time taken by the time it takes for the capacitor to charge from 0 to 2/3 of BCC. Okay, is this. So what is the difference between T2 and T1? Help me here. What is the difference between T2 and T1? So RC, I think I have it in the next slide. Yeah, but that's okay. So RC ln3 minus ln3 over 2. So what do I get here? RC ln3 over 2. Oops, not that. I made a mistake. This can be rewritten as ln 3 over 2, which is RC ln 2. This 3 and 3 cancel, it goes up, right? This is this is my T. This is time for the charging. This is charging period. Why do I call the charging period is T2 minus T1? Why not entire T2? Let me show you here. Let me go back here. So when my T2 is, so T2 is charging up to B equals 2/3 of BCC. The time taken is T2, right? Okay. Look, when the voltage is, let's say this is 3 volt. So it doesn't go, it just oscillates between 3 and 6. That's what I'm saying. So this guy oscillates between 3 and 6. Okay, it doesn't go to 9 volt, it doesn't go to 0 volt. Okay, it happens between 0 and 3 and 6. You know why? Let's see. Okay, this is 3 volt. This is let's say 2 volt, right? This is 2 volt. This is 2 volt. This is 2 volt. This is 9, right? This is your 6. This is your 3, right? So what is the output here? This is 1, right? So this is 0. You get 0. This is 0. So this is open. So the charging process, it is charged, right? Since this is open, it charges, okay? Charges 0 to, from 0 to 2 volt, let's say. 0 to 2 volt, it charges, okay? Then 3, let's say this is the initial process, right? Then what if this is 4 volt, what happens? 4 volt, up to go up way up to until up to, when it is 4, what happens? This is 3, right? This is 3, this is 4. You get 0 and you have 4 here too. So this is also 0. So it holds the state all the way to 6. It holds the state. Okay. Now when it is 7 volt, when it is 6, what happens? When it is 6.1, let's say this is 6.1. This is 6.1. So what happens? This is your 6, this is your 6.1. Will that happen? Let's see. When I say 6.1 is slightly more than 6, okay, that's what I meant. So when it is slightly more than 6.6, then what happens? You get here 1.
Yep.
Okay. So this one sets, right? This is 1. When this is 1, this is closed. You understand? This is closed. That's why this guy is closed. Then the capacitor no longer charges. It starts to discharge here. See, as soon as it reaches 6, it starts discharging, meaning the voltage comes down now. After 6, it comes down. Okay. So now the thing is, when it reaches, let's say 2.9, it comes down, right? When it reaches, because when the capacitor discharges, the voltage going down, right? Let's say it goes to 2.9, slightly less than 3. What happens? When this is 2.9, what happens? This is 3, right? This is 2.9. So this is 3. What happens here? So this is greater than that. Then this gives me 1. Then your reset is 1. This means this is 0. And this is open now. This is open. This guy is open now again. See? This guy is open. Then it no longer discharges. It charges again. It charges again because this is open. So it charges again. Then when it reaches, at 3, it again discharges. Then again it charges. See, it fluctuates between 3 and 6. Okay, it fluctuates between 3 and 6. That's why to find the discharging time, you have to subtract. Discharging is between 3 to 6, right? Sorry, charging is between 3 to 6. That's why our charging time is T2 minus T1. T2 is for the voltage to reach 6. T1 is for the voltage to reach 3. That's why charging time is between T2 and T1. Yeah. So T2 minus T1 is the charging time. How about discharging time? In the same way, your discharging time is, in the same way your discharging time will be so your discharging time will be, okay, let me finish the charging time. So your charging time is T2 minus T1 equals RC this, so which is this, right? But during the charging process, what are the resistors here in the charging process? You have two resistors in series. That's why your R is RA plus RB. That's your charging time. Okay. In the same way, discharging time will be, if you do the same method again, your discharging time will be RB ln2. It makes sense because it discharges through RB, right? So that's why you have RB ln2. And this one charges through RA and RB. That's why you have RA plus RB ln2. Then what is the total time period for charging and discharging? Charging, discharging. This is discharging. So ln, this is ln2 is 0.693, by the way. Okay, this is your ln2. So this is your discharging time. This is your charging time. Add them together. That's the total time period. This is the formula we'll be using in the next lab. Guys, unless you have any questions, I'm done with digital. Everything with digital is done. So let's talk. Yeah, go ahead.
I don't think anybody's